moment we learned about harmonic oscillation, superposition of different harmonic oscillations. Now we can think about a traveling wave packet. Suppose a transmitter at z equal to 0 transmits waves, radiations in the form of pulse for a small duration. This pulse propagates through the medium. That means now the pulse is a traveling wave packet or wave group. Now you can think that there is a frequency band, because already we see that when a pulse is formed there is a frequency band delta omega. And in the case of traveling wave, its wave vector k is a function of omega. That means there is a dispersion relation between the wave vector k and the frequency components omega. This relation is called dispersion relation. So in the case of traveling wave, there is a wave vector band delta k corresponding to delta omega of frequency band. That means the wave packet moves with group velocity such that there is a band of wave vectors delta k corresponding to the frequency band delta omega. That is delta k equal to dk by d omega into delta omega into delta omega. Okay, there's a relationship. You can write a relationship like this. But what is this 0? This is the corresponding to the maximum center frequency. That is, for a center frequency omega 0, there is a center wave vector k0. That means this k0 equal to k of omega 0. So our frequency band delta omega has a center frequency omega 0. Corresponding to this center frequency, there is a center wave vector k0 such that k0 equal to k of omega 0. So what is this expression represents? This is the inverse of group velocity of the wave packet measured about the center frequency omega 0. That is, this term equal to delta omega by Vg. Vg represents group velocity at around the frequency component omega 0 or the center frequency. So you get this equation. You can call this equation as your equation. So our traveling wave packet propagates through the medium through a distance delta z. So delta z distance traveled by the wave packet approximately with the time group velocity into delta t. Velocity into time represents the distance travelled. So delta z approximately equal to Vg into delta t. So now we can multiply both sides of this equation with delta k. What is delta k? It is the band of wave vectors corresponding to the frequency band delta omega. Okay, so now we can multiply both sides of this equation with delta k. So you get delta k delta z approximately equal to delta k Vg delta t. What is this delta k Vg? We learned earlier in our previous lectures that this delta omega, delta t is always greater than or equal to 2 pi. So, this condition is equivalent to delta k delta z in the case of a travelling wave packet. So, we can write this expression as delta k delta z equal to delta omega delta t. This is greater than or equal to 2 pi. Okay, now we know that k equal to 2 pi by lambda. K equal to 2 pi by lambda. For further simplifying this equation, let sigma equal to 1 by lambda. That is, inverse of wavelength is called as sigma. So, this k becomes 2 pi sigma. We can use this equation in this expression. So, what happens? 2 pi delta sigma delta z equal to delta omega delta t, which is greater than or equal to 2 pi. Now we can cancel 2 pi from both sides and we get that delta sigma delta z greater than or equal to 1. This is the equation for a travelling wave packet. In the case of a simple harmonic oscillations, which superimposed state of simple harmonic oscillations or pulse, we learned that delta nu delta t greater than or equal to 1. In the case of travelling wave, we can express this equation in this form: delta sigma delta z greater than or equal to 1. So, when this term is equal to 1, this happens, as we already said in this case, all frequency components starts with same amplitude and same phase. Usually, as the wave propagates through the medium, each component moves with different velocity and the group velocity itself varies. In this case, we get delta sigma delta z greater than 1. More general cases, delta sigma delta z greater than 1. If all the initial conditions are, if we arrange all initial conditions such that all of the components have same frequency, same amplitude and same phase, then we get the minimum condition, delta sigma delta z equal to 1. Otherwise, it's always greater than 1, corresponding to the broadening of the wave packet. So, you can think that if the travelling wave moves through a dispersive medium, its group velocity varies, and in that case, delta sigma delta z greater than 1. Otherwise, in the case of non-dispersive medium, the wave packet propagates through the medium such that its shape preserves. In that case, this condition delta sigma delta z equal to 1. Okay, so we can conclude now what happens to a travelling wave packet. If a travelling wave packet moves through a dispersive medium, its group velocity varies, and corresponding to this, delta sigma delta z is greater than 1, leading to the broadening of the pulse. As the wave pulse propagates through the medium, it gets broadened. But in the case of a non-dispersive medium, it moves with constant group velocity. Its group velocity never changes with variations in the frequency or like that. So in that case, the wave packet or the pulse moves through the medium, preserving its shape. This is all about the traveling wave packet. So we can check the Fourier analysis of a traveling wave packet. For that, assume that a transmitter at z equal to 0 transmits radiations into a homogeneous continuous medium. The disturbance or the radiation propagates through the medium. So, in this context, the wave or the radiation produced by the transmitter is a traveling wave which propagates through a homogeneous and continuous medium. Okay, now suppose at z equal to 0, the wave is represented by psi 0 t equal to f of t. That means initially at z equal to 0, the amplitude of the wave is represented by f of t. Okay, this f of t can be with any form. So let it be non-periodic. So we already found that if this f of t is a non-periodic function, we can represent it using Fourier integral. So I can write the Fourier integral form here. That means f of t equal to integral 0 to infinity a of omega cos omega t d omega plus integral 0 to infinity b of omega, here it is sin omega t, b of omega cos omega t d omega. Okay, so sin here f of t is a series of sin omega t and a series of cos omega t, continuous superposition of harmonics. Okay, now suppose at the later time we assume that the wave is traveling through the medium. That means the propagation of this function, the wave function at a later time t is represented by psi z of t. How can you get this psi z of t? We have only one option. That means we know that here z equal to 0, so the series contains sin omega t and cos omega t. But if there is z, that means the wave propagates through the medium, omega t transforms to omega t minus kz. As we all know, this k depends on frequency omega, so this expression is like this: omega t minus k of omega z. So replacing omega t with this expression omega t minus k of omega z, in this equation we get psi z of t. That means psi z of t equal to integral 0 to infinity a of omega sin omega t minus kz d omega plus integral 0 to infinity b of omega sin omega t minus k of omega z d omega, here cos omega t minus k of omega z d omega. So from this expression to this expression, we have to change this argument from omega t to omega t minus kz. So we get the expression for a traveling wave packet. passing through a medium like this. Now we can analyze this equation in two contests. First one is dispersive medium and the second one is non-dispersive medium. So we can move on to case 1, dispersive medium. In the case of a dispersive medium, we already learned that each frequency component moves with its own phase velocity. So here the angular wave number varies with angular frequency omega. That means in this contest k is equal to k of omega and each frequency component moves with its own phase velocity. Here it is represented by V phi. V phi equal to omega by k of omega. So what happens to the pulse? That means here we already found that psi of t equal to integral 0 to infinity a of omega sine omega t minus k of omega z d omega plus integral 0 to infinity b of omega cos omega t minus k of omega z d omega. Now each frequency component, each harmonic moves with its own phase velocity through the medium. The medium is dispersive, so the wave packet or the pulse cannot maintain its shape as the wave propagates through the medium. That means here the shape of the pulse varies. Why? Because each frequency component moves with its own frequency due to the dispersive medium. So altogether the wave packet cannot maintain its shape as it propagates through the medium. So the wave cannot maintain its shape. Its shape varies as the wave propagates through the dispersive medium. In the second case, the case of non-dispersive medium, each frequency component has same phase velocity. That means V phi equal to V, which is equal to omega by k. So each component, all the frequency components moves with same velocity v, which is given by omega by k. So the expression for pulse psi z of t equal to integral 0 to infinity a of omega sine omega t minus, here there is v equal to omega by k. From this equation we can substitute for k. All of you know that here k equal to omega by v. Okay, substituting this here, you get that omega z by v d omega plus integral 0 to infinity b of omega sine cos omega t minus z by v d omega. Okay, here also you can write like this. That means omega into t minus z by v. Okay, this equation for a pulse in a non-dispersive medium. So what happens to pulse here? Here the pulse keeps its shape throughout its propagation through the medium. So there is no change in shape. That means the shape of the pulse remains same. As the wave propagates through the medium. As the wave propagates through the medium. So, in the case of a traveling wave, if the wave propagates through a dispersive medium, the shape of the pulse changes because each frequency component moves with different velocity. But in the case of non-dispersive medium, all frequency components moves with same frequency and the pulse maintains its shape throughout its propagation through the medium. Now we can check what is a classical wave equation. In our previous too many lectures, we learned so many properties of waves, but never we discussed about its equation. Now it is the time for discussing classical wave equation. So consider the harmonic component of the form psi of t equal to a cos omega t minus kz. As all of you know, these types of harmonics superimpose together and form wave packets. We already learned that. So now we can use this single harmonic function because psi of t equal to a cos psi z of t. Psi z of t equal to a cos omega t minus kz. This is a traveling wave of this form. Now, suppose we taking its partial derivative dou psi by dou t. So, taking derivative of this function with respect to time t. So, what we get? We get a omega minus sin omega t minus kz. Okay. Now once again taking differential with respect to time dou square psi by dou t square. This is equal to again you get minus a omega square cos omega t minus kz. Okay, this is equation 1. This is equation 1. Now we can take the derivative with respect to z of this equation. So dou psi by dou z equal to minus ak minus sin. Minus and minus cancel each other. So we get ak sin omega t minus kz. Now taking second derivative dou square psi by dou z square. This is equal to again minus a k square cos omega t minus kz. Okay. So we get two equations like this. In both these equations, from these two equations, equations 1 and 2, in these two you can see that one side is cos omega t minus kz. So we can compare these two equations. So, from equation 1, dou square psi by dou t square equal to minus a omega square. Now, the cos term is replaced from this equation 2. So, minus a k square dou square psi by dou z square. See, so these two terms cancels out. You get v square dou square psi by dou z square, v phi square. From where this v phi comes? Because omega by k represent phase velocity. So omega square by k square represent phase velocity square, v phi square. So you get the equation dou square psi by dou t square equal to v phi square dou square psi by dou z square. Now, in the case of non-dispersive medium, we know that this v phi is a constant which is given by the velocity v. So, this equation takes the new form dou square psi by dou t square equal to v square dou square psi by dou z square. See, this equation is called classical wave equation. If each frequency comes, in the case of non-dispersive pulse, non-dispersive medium, whole frequency components moves with same velocity. So this equation obeyed by the wave. So this equation is called the classical wave equation. So in this lecture we discussed Fourier integrals, travelling wave packet, Fourier analysis of travelling wave packet in two contexts, dispersive medium and non-dispersive medium. Hope that all of you get what we learned in these sections and learn well. Thank you.